In this video, I'll be discussing the topic of the sound of black hole collisions. To start with, a black hole is a celestial body with gravity so strong that not even light can escape from it. When a star approaches a black hole, it is torn apart by the strong gravity and gradually sucked in. The gas of the star being sucked in rotates at ultra-high speeds around the black hole, forming a gas disk known as an accretion disk. Due to the friction between the high-speed moving gases within the accretion disk, it becomes superheated and emits strong X-rays. So, what happens when black holes collide with each other? Most black holes are the end result of the evolution of massive stars. When a star with about 30 times the mass of the Sun experiences a supernova explosion at the end of its life, the star's interior collapses into a black hole. Observations show that many very bright massive stars exist as binary systems. If each star in a binary system becomes a black hole, a binary system of black holes is created. The two black holes in a binary system are drawn together, describing spiral orbits. As they draw closer, the distortion of the space around them increases until they finally merge into one black hole. Immediately after the merger, the black hole vibrates intensely, losing energy and gradually settling down. During the process of black hole merger, strong gravitational waves are generated. Gravitational waves are distortions of spacetime that propagate as waves. According to Einstein's theory of general relativity, gravity is understood as a distortion of spacetime. The Earth orbits the Sun, and the mass of the Sun distorts the spacetime around it, and the Earth is subject to gravity due to this distortion. When a mass-bearing object moves, the resulting distortion of spacetime propagates as a wave at the speed of light. When gravitational waves pass through, space stretches and contracts. However, gravity is very weak, so the effect of gravitational waves is very small. For example, even swinging a dumbbell generates gravitational waves, but their power is extremely weak. Planets orbiting the Sun or binary stars do not generate gravitational waves at levels that humans can detect. The moments when gravitational waves are most likely to be detected are when very dense celestial bodies, such as black holes or neutron stars, merge. The merger of black holes is believed to occur once every million years in our galaxy. It is an extremely rare phenomenon, but such a major event can be detected even if it occurs a billion light-years away. Since there are millions of galaxies within that range, it is estimated that we can observe gravitational wave events a few times a year. The first time humans captured a gravitational wave event was on September 14, 2015. On this day, gravitational waves were almost simultaneously observed at two observatories of LIGO, Laser Interferometer Gravitational Wave Observatory. This signal was confirmed to be a gravitational wave from the merger of two black holes that occurred about 1.3 billion light-years away from Earth. LIGO converted the observed gravitational waves into sound waves and made them publicly available, which I will introduce. The low sound that plays twice at the beginning matches perfectly in frequency with the gravitational waves generated by the collision of black holes. The high sound that plays twice next has its frequency increased to fit within the human hearing range. Although it's a momentary event, as we approach the moment of the black hole collision, the distance between the black holes also gets closer, and you can see that the frequency of the sound wave rises to a high tone and the amplitude becomes larger, creating a louder sound. The gravitational wave signal observed by LIGO was just 0.2 seconds in time. So, what did we learn from analyzing this 0.2-second gravitational wave signal? The waveform of the observed gravitational wave can be divided into three main stages. The first stage is called the inspiral stage. This is the stage where two black holes are orbiting each other. While emitting gravitational waves, they approach each other due to the loss of energy. As a result, the orbital period quickens, the gravitational effect strengthens, and they emit higher gravitational waves with larger amplitudes. Consequently, over time, the frequency and amplitude increase, and a characteristic waveform appears. The second stage is the merger stage. This is the stage where the two black holes merge, emitting very large gravitational waves. The final stage is called the ring-down stage. This is the stage where the newly formed black hole from the merger loses energy while emitting gravitational waves, and eventually settles down. From the waveform of the observed gravitational waves, it was found that the gravitational wave event in September 2015 was a phenomenon in which black holes with 36 and 29 times the mass of the Sun merged, creating a single black hole with 62 times the mass of the Sun. According to Einstein's theory of relativity, mass can be converted into energy. The mass equivalent of 3 suns that was lost was instantly emitted as energy in the form of gravitational waves. The energy of these gravitational waves is more than 10 times the energy of the light emitted by all the stars and galaxies in the observable universe within 46.5 billion light-years from the Earth. This truly is an astronomical phenomenon of a different dimension. Furthermore, it was found that just before the merger, the black holes were rotating at about 60% of the speed of light. In addition, let me introduce the sound made by the supermassive black holes at the center of galaxy clusters. Sound, in general, is a wave that propagates through matter. We hear waves propagating through Earth's atmosphere as sound. It is generally understood that sound does not propagate in space because there is no medium like the Earth's atmosphere for waves to propagate. The sound of the black hole merger introduced earlier also perfectly matches in frequency, but it is a conversion of the waveform of the observed gravitational waves into sound waves. However, NASA contends that this common understanding is a misconception. For instance, in a galaxy cluster, a large group of hundreds of galaxies, there is gas present at high density, albeit not as much as in Earth's atmosphere, and this gas becomes a medium for transmitting sound. In particular, in the Perseus cluster, located about 220 million light-years away in the direction of the constellation Perseus from Earth, pressure waves emitted from the supermassive black hole at its center are propagating through a large amount of extremely hot gas surrounding it. This can be perceived as a sound wave on a very macro scale. However, this understanding captures the subtle variations in gas density on a truly macro scale of tens of thousands of light-years as sound waves, so the sound is too low to be audible to humans in its original form. Therefore, the pitch of the sound is significantly increased so that it can be heard by the human ear. Now, I am going to play the actual sound that was made public. Be aware, it's quite a formidable sound, so listen carefully. This sound is published after capturing the variations in the density of gas in different directions from the black hole at the center of a galaxy cluster as sound waves, as revealed by the Chandra X-ray Observatory, and editing it into a sound that is actually audible. As previously mentioned, the original sound is too low to be heard by the human ear, but it has been raised by 57 to 58 octaves to make it audible. Raising by 1 octave doubles the frequency, so this sound has had its frequency increased by 2 to the power of 58 times the original sound, that is, 2.88 quintillion times. And, By this sound wave propagating through the surrounding gas, the temperature of the gas is maintained at an ultra-high temperature of 30 million degrees over a long period of 1 billion years. It is precisely because the temperature is so high that the variations in gas density are discerned through the X-rays emitted from here, and we are able to enjoy it as a sound that is actually audible to human ears. Thank you for watching this video. Please subscribe to the channel and give it a thumbs up. Let's meet again in the next video. Bye.